Hello everyone, and welcome to our channel, Mootechie. It's so wonderful to have you here as we dive into the fascinating world of chemistry. Today, we're going to explore a fundamental concept that helps us understand our world, from the food we eat to the products we use. Get ready to unlock the secrets of pH and pOH in a student-friendly way. Now, let's begin with an introduction to what pH and pOH actually are. pH measures acidity based on the concentration of hydrogen or hydronium ions in a solution. On the other hand, pOH measures basicity based on the concentration of hydroxide ions. You might be wondering, why does this matter? Well, these concepts are crucial in biology, environmental science, food science, cleaning products, and of course in laboratories every single day. To think about it in everyday terms, we know acids often taste sour, while bases can feel slippery and taste bitter. Moving forward, let's look at the pH scale itself. The pH scale typically runs from 0 to 14. It's a logarithmic scale, which means each whole number change represents a 10-fold change in hydrogen ion concentration. A pH of 7 is neutral, like pure water at 25 degrees Celsius. Anything below 7 is acidic, and anything above 7 is basic, or alkaline. Let's look at some common examples on this scale. At the very low acidic end, around pH 1, we have stomach acid. Around pH 3, we find vinegar. Coffee is a weak acid, sitting around pH 5. Right in the middle, at pH 7, we have pure water. Moving into the basic range, baking soda has a pH around 8. Soap is around 9 or 10. Ammonia is about 11, and strong bleach can be around pH 12.5. As we continue, let's understand the math behind pH. The formula is pH equals negative log base 10 of the hydrogen ion concentration, where the hydrogen ion concentration is in moles per liter. This is an inverse relationship. If you know the pH, you can find the hydrogen ion concentration by calculating 10 to the power of negative pH. Because it's a logarithmic scale, a change of 1 pH unit means a 10 times change in ion concentration. So a pH of 4 is 10 times more acidic than one with a pH of 5. And a pH of 3 is 100 times more acidic than a pH of 5. Let's try an example to find pH from concentration. If the hydrogen ion concentration is 1.0 times 10 to the negative third moles per liter, we plug it into the formula. pH equals negative log of 1.0 times 10 to the negative third. This calculates to negative times negative 3.0, which is positive 3.0. So the pH is 3.00. Now, let's go the other way and find concentration from pH. If the pH is 5.00, then the hydrogen ion concentration equals 10 to the power of negative 5, which is 1.0 times 10 to the negative fifth moles per liter. Following this, let's get to know the pOH scale. pOH is defined as negative log base 10 of the hydroxide ion concentration. And inversely, the hydroxide ion concentration equals 10 to the power of negative pOH. A lower pOH means the solution is more basic because it has more hydroxide ions. Conversely, a higher pOH means the solution is more acidic because it has fewer hydroxide ions. It really mirrors the pH scale, but it tracks the hydroxide ions instead. On this scale, which also typically runs from 0 to 14, a pOH of 0 is the most basic, and a pOH of 14 is the most acidic. At 25 degrees Celsius, a neutral solution has a pOH of 7. And here's the key relationship. At this temperature, pH plus pOH always equals 14. Now, let's bring it all together and look at the characteristics of different types of solutions. First, acidic solutions. They have a pH of less than 7 and a pOH of greater than 7. The relationship between ions is that the hydrogen ion concentration is greater than the hydroxide ion concentration. They often have a sour taste, are proton donors, and can react with metals. For example, a solution with a pH of 3 has a pOH of 11. Its hydrogen ion concentration is 1.0 times 10 to the negative third molar, and its hydroxide ion concentration is 1.0 times 10 to the negative 11th molar. Next, neutral solutions. They have a pH of exactly 7 and a pOH of exactly 7. Here, the hydrogen ion concentration equals the hydroxide ion concentration. This represents a perfect balance between acidic and basic properties. So at 25 degrees Celsius, both the hydrogen and hydroxide ion concentrations are 1.0 times 10 to the negative 7th molar. Finally, basic solutions. They have a pH of greater than 7 and a pOH of less than 7. In these solutions, the hydrogen ion concentration is less than the hydroxide ion concentration. They often taste bitter, feel slippery to the touch, and are proton acceptors. For example, a solution with a pH of 10 has a pOH of 4. Its hydrogen ion concentration is 1.0 times 10 to the negative 10th molar, and its hydroxide ion concentration is 1.0 times 10 to the negative 4th molar. So, what links pH and pOH so directly? At 25 degrees Celsius, pH plus pOH equals 14.00. This is because the water dissociation constant, Kw, is 1.0 times 10 to the negative 14th. This is such a useful relationship. If you know one value, you can instantly find the other. A quick but important note. This sum of 14 is specific to 25 degrees Celsius. It changes slightly with temperature. Let's see it in action with an example. If the pH of a solution is 9.20, then the pOH is simply 14 minus 9.2, which equals 4.8. To really make this stick, let's connect it to some real-world examples. Strong acids include stomach acid at around pH 1.7, lemon juice at about 2.2, and vinegar at 2.9. Weak acids are things like coffee at pH 5, oranges at 3.5, and soda at around 3. Near neutral substances include milk, which is between 6.5 and 6.8, pure water at exactly 7, and our blood, which is slightly basic at about 7.4. Weak bases are seawater around 8.1, baking soda at 8.3, and hand soap between 9 and 10. And strong bases include ammonia around pH 11, bleach between 12 and 13, and drain cleaner can be as high as pH 14. So imagine a scale from very acidic to very basic. On one end, we have stomach acid and lemon juice. Then we have things like baking soda and hand soap in the middle of the basic range. And on the far end, we have powerful cleaners like bleach. Now, let's put our knowledge to the test with some calculations and practice. First, let's go from hydrogen ion concentration to pH and pOH. The formula is pH equals negative log of the hydrogen ion concentration. In our first example, the concentration is 1.0 times 10 to the negative third molar. We apply the formula, pH equals negative log of 1.0 times 10 to the negative third. This calculates to negative times negative 3.0, which is positive 3.00. So the pH is 3.00. Now, we use the relationship pH plus pOH equals 14, so pOH equals 14 minus 3.0, which is 11.00. For our second example, let's start with a pH of 8.50 and find the hydrogen ion concentration. We rearrange the pH formula. Hydrogen ion concentration equals 10 to the power of negative pH. So that's 10 to the power of negative 8.50, which equals 3.16 times 10 to the negative 9th molar. Then we find the pOH. 14 minus 8.5 equals 5.50. Next, let's work from hydroxide ion concentration to pOH and pH. The formula is pOH equals negative log of the hydroxide ion concentration. In example 3, the hydroxide ion concentration is 2.0 times 10 to the negative 4th molar. We apply the formula, pOH equals negative log of 2.0 times 10 to the negative 4th. We can break this down. Negative log of 2.0 is about negative 0.30, and negative log of 10 to the negative 4th is positive 4. So, negative 0.30 plus 4 equals 3.70 for the pOH. Then pH equals 14 minus 3.70, which is 11.30. For our final example, let's start with a pOH of 2.20 and find the hydroxide ion concentration. We rearrange the pOH formula. Hydroxide ion concentration equals 10 to the power of negative pOH. So that's 10 to the power of negative 2.2, which equals 6.31 times 10 to the negative third molar. Then we find the pH. 14 minus 2.2 equals 11.80. As we wrap up, let's review the key takeaways from our session. First, the formulas. pH equals negative log base 10 of the hydrogen ion concentration, and pOH equals negative log base 10 of the hydroxide ion concentration. Remember the temperature relationship. At 25 degrees Celsius, pH plus pOH always equals 14 because the water dissociation constant is 1.0 times 10 to the negative 14th. And don't forget the power of the scale. Each single unit change in pH represents a tenfold change in hydrogen ion concentration. In terms of acidity and basicity, a pH less than 7 is acidic, equal to 7 is neutral, and greater than 7 is basic. To build your intuition, think about everyday examples like sour lemon juice at pH 2, neutral pure water at pH 7, and slippery soap at pH 9 or 10. And a final calculation tip, always be mindful of the temperature conditions and pay close attention to significant figures in your work. Thank you so much for learning about pH and pOH with me today. I hope this journey through acidity and basicity has been both enlightening and enjoyable. Thank you. See you in the next class.